I think with that we can start. So the first speaker of today's session is Alejandra Castro from University of Cambridge, and she's going to tell us about holographic aspects of symmetric product orbifolds.
Thank you. And you'll keep time?
I will keep it.
Okay, because we're supposed to keep it short, and I want to set up a good example. So thank you so much for the invitation. I'm very happy to be here, and I'm very happy to tell you a bit about my work. Sorry, I have to decide which one will go on the left hand and which one on the right hand. Okay, so before we start, this is a talk with a very long title. I wanted to acknowledge that what I'm going to be telling you today is based on a collection of work that has been happening for, I don't know, close to 8 or 10 years with a variety of people. So here I'm listing my collaborators, and I highlighted and read the most junior people in this collaboration, basically people that don't have permanent jobs yet, but they're fantastic physicists, so I hope you keep an eye on them. But okay, so what is the aim of this talk? What do I want to do? So I want to think that this is an audience of experts, so I'm not going to spend time on introductions and things. But this is a talk about ADS-CFT as the title, as the word holographic means. And I'm going to take a CFT perspective on how to define ADS. And so from that point of view, the main question that I have that is going to be governing this talk is basically try to understand which conformal field theories can capture classical geometrical properties of gravity. Okay? This is the question I have. Okay, I want to understand what are the very specific properties that define that CFTs. Those type of CFTs, I'm going to abuse language, and I'll call them holographic CFTs. Okay? I know there's a sense in ADS-CFT where you would have said any conformal field theory has a dual. It might not be a dual that you want, but just to keep things, the terminology brief, I will call a holographic CFT basically a conformal field theory whose dual gravity theory has a low energy effective field theory description. Okay? Now, so we all are accustomed to various aspects of ADS-CFT, and so you will tell me, well, some properties that those CFTs needs to have, some of the defining properties are first, that there has to be a large central charge or a large n parameter. Why do we want that? Because in this theory of gravity, there will be black holes, and we need a theory that has a large number of degrees of freedom. We also need what's called a sparse spectrum. This is basically a condition on light operators that are not controlled by n, and this is very important so that I can use the words basically a low energy effective field theory description. So it's tied to that requirement, that I can't have too many fields in my low energy description. Then there's a more fancy condition, the factorization of correlation functions, which also goes under the term that the CFT has a generalized free field description in some sectors, and so on. But the question I have basically is, how many conditions do I need to impose? Here I listed a few that we know are part of what works in the current dictionary and things that we know. But is this all I need to impose? How stringent are these conditions? And basically, if these are the conditions, can I just go and engineer a CFT that meets this criteria? Okay, so having the capacity of doing this really will show us that we understand in and out what ADS-CFT is and how to define quantum gravity via the holographic correspondence. And so I'm not going to give you an answer to this question. This is a really difficult question, and all of these together. But I want to kind of entertain the question. Okay, so let's just kind of dive into it. What would it mean to answer these questions? And so for us, what it meant was like, okay, so you want to engineer CFTs that meet this criteria, pick a CFT that maybe, or a family of conformal field theories that might be interesting. Okay, so here comes the other part of the title, symmetric product orbifolds. And so this is the type of theories, conformal field theories in 2 dimensions that I like. Okay, So what are these theories? They have a very long name, but they're actually not that complicated. So these theories are basically, so the quick definition of them is basically grab your favorite CFT that I'm calling here C, okay, and then tensor it n times, okay? You do that. What you will get there, so the reason why I'm tensoring my favorite CFT n times is because I wanted some parameter, some large n parameter that I'm going to take to infinity. So I'm going to consider, this is a very easy way how to get large central charge in CFTs. You just tensor the theory again. Now you know that this is kind of like not a very interesting thing to do. It will not meet, for instance, the sparseness criteria and things like that I imposed. And so in order to remove basically, like if you want to think about it as like the redundancy of like, oh, the positions of the copies are indistinguishable, you basically mod out by the permutation group. So you basically say the positions of the copies should not be important. And so that's what you can view as gauging in this context, okay? And this is what defines CM. So it's basically the tensor product of n copies of the theory modded out by the permutation group, okay? Pretty big name for something that is quite simple. Now, there's two things that you need to know about this. So once you do this process of orbifolding, produces two types of states then in your theory. You will have what's called untwisted sector states. Basically, they're states that are going to be invariant under the permutation group, and what's called twister sector states that are basically states labeled by conjugacy classes of the permutation group. If you want, these ones are like gauge invariant operators, and these are things that transform under it. If you want to have an analogy with something like SUN. Okay, very good. Now, why did I pick this? Why is this the type of conformal field theories that I'm going to start asking questions on these lines? Well, there's an appeal because they have a lot of very nice mathematical and analytical properties that allow me to control various aspects of the theory, as I'll highlight. It's familiar, so for those of you that come from a string theory context, but specifically from string theory and ADS3, this is basically the D1, well, various ingredients here show up in the D1, D5 CFT. And there's a utility to them because they have a lot of features that are compatible with ADS CFT, broadly speaking, okay? So this is why we started looking at these type of theories. Now, what I want to do in the rest of this talk is basically I want to understand what do these type of theories teach us about the conditions for having a holographic CFT? So what can I learn about this list of what am I supposed to impose? How am I supposed to construct a holographic theory? And so the way that I'm going to structure the rest of this talk is basically, it's in two parts. So I'll first tell you in the context of symmetric product orbifolds, what are differences and similarities with low energy gravity? So how do they look like a low energy theory of gravity and why they don't look like a low energy theory of gravity? And then I'll tell you about how we classify this set of theories. Okay, so let's start with the differences and similarities. So I'm going to bundle them both together. So let's first talk, in this context, what I'm going to summarize to you as I talk about these differences and similarities, I'm basically going to tell you properties of symmetric product orbifolds that are universal. That these are going to be properties that I don't care what you put here as a seed theory. So what are you tensoring? Every single symmetric product orbifold will satisfy these properties, okay? And that's what's going to teach me about how they look like gravity and why they don't look like low energy gravity, okay? So they're very, very universal properties. Okay, so what are the differences with low energy gravity? By the way, you're free to interrupt me with questions since I feel like I'm speaking very fast. Very good.
Can you already tell us how the central charge of this theory scales with n?
It's linear with n. It's n times, so if this guy has a central charge, let's say C naught, the total central charge is n.
The scaling with n comes from just the number of copies.
Exactly, exactly. So
any particular reason you didn't choose n to be the rank of some non-abelian group or?
No, this is all the information that you have. It's basically what the number of copies you have. That's it. It's way simpler than gauge theories. I have to specify way less information in this context. So yeah, so the central charge just grows linearly with n, and then you just take n to infinity, and that's what a lot of these computations do. And it's simple as that. Any other questions? Okay. So here are three things why these theories are not describing, the duals are not low energy gravity. The first one is that you can have higher spin currents. Okay, so for any value of n that is basically bigger than 1, you can construct a tower up to n of higher spin currents, and if n goes to infinity, then you will have infinitely many higher spin currents. So here I gave you an example of, for instance, the spin 4 current, just so you can have an idea of like how do you construct this higher spin current. So here Ti is the stress tensor of a single copy, and basically you square it, okay? But you can do that in any CFT. So for instance, these first two terms here, it's something that you can write in any given CFT, but this is not a primary. This will be a descendant of the stress tensor. And what's special in symmetric product orbifolds is that you can add a term where you have terms that are in different copies, and this allows you to basically build a primary that is a spin 4 primary, okay? And then you can imagine, I just did it with like 2 insertions of the stress tensor, keep on adding more insertions, and basically constructing the appropriate thing. This is an exercise. It's a tedious one, but it's something that you can systematically do, okay? So they have higher spin currents, and we know that low energy effective theories of gravity do not have higher spin currents. Second, there's a Hagendorn growth of light states. So this is something that was shown back in 2011 by Christoph Keller. And basically the statement is that light states are basically, I'll define them more as we go along, but for the context here, they're states whose conformal dimension is less than c/12, or if you want, depending on how you measure things, they're light because the conformal dimension will not grow with the central charge of the theory. But these states basically have an exponential growth, okay? And this type of exponential growth is not compatible with a QFT on a curved background, okay? So if you have a quantum field theory on a curved background, the growth is always, this power here is not 1, it's always less than 1. It's basically d minus 1 divided by d, if d is the number of dimensions that your conformal field theory lives in, okay? So this is why also I know that this is not a low energy effective field theory from the point of view of the dual. And then there's a third reason, but this reason is actually related to the first one, so I'm cheating here a little bit. But basically these higher spin currents basically spoil chaos and the out-of-time order correlator. And so this type of correlator will not decay in time, which is something, it's a more fancy kind of criteria that you would put in your low energy theory of gravity, but it's basically a consequence of the first one, okay? So those things already tell me, Alejandra, why are you picking these theories to understand what a holographic CFT is, where clearly it's not a low energy theory of gravity? But okay.
These currents, do they satisfy some known algebra?
Oof, that's an excellent question. It's really tough to figure out.
Perhaps in the limit of large Z.
It's even, it's been, nobody has been able to work it out. So WN algebras are disgusting. It's not quite WN or H or W infinity or like the ones that usually appear in higher spin literature. And nobody has given a proper characterization. It's really cumbersome. But you just know that the currents exist. That's quite easy to establish. But yeah, what is the exact nonlinear algebra? It's tough. Yeah, there's certain cases. So for instance, because sometimes the seed theory also provides like currents. So for instance, when you are in the D1, D5 picture, and the seed theory is a free theory, so it's like just 4 bosons and 4 fermions. There are certain limits there that you can take where like people like Gabriel and Gopakumar have described, like have given you some description of what is the expected algebra, but it's very specific, and it's not it's not fun to do either. But yeah, very good. So those are the differences, and usually, like based on these properties, if you ask, okay, so what is the dual of a symmetric product orbifold? Usually the dual look like the tensionless limit of a string theory, or look like a higher spin gravity, okay? Not my low energy theory of gravity that I wanted to start talking about. But this is also, again, kind of a hand wavy. I can't demonstrate to you like, oh, it will be this. But these are features that we know that appear in a tensionless string theory or in a higher spin theory. So it's kind of like, okay, it should go along those lines. But now let's see how they do look like a low energy gravity. So why are they good mimickers of low energy gravity? Okay, so these are properties. Because I'm interested in how they look like low energy gravity, I will always be, everything that I say here, you do have to have in mind that it's a large n limit of the theory. Okay, so the first property is this factorization of correlation functions. So basically here, I'm looking at operators that we call light, basically operators whose conformal dimension is finite in the limit n going to infinity. And here I'm writing down the formula for what's called a single trace operator. So the number of traces in this context is basically the number of independent sums that you need to symmetrize an operator as you insert it in a copy. Okay? So a single trace operator in this language is basically where you only needed a single sum, and that can be either an untwisted operator where you just have it a single copy of it and then you symmetrize it, or something, a twisted operator where you use just a single cycle for the twisting. Okay? So basically, very similar to what happens in n equal 4 super young males in higher dimensions. What you see there is that correlation functions of single trace operators, basically the connected part of that correlator decays with n in a suitable fashion. Okay? So this is what people call the factorization property of the correlation functions. And symmetric product orbifolds obey it, which is great. Okay? Nice property of symmetric product orbifolds. Now, a more non-trivial property related to the phase structure and the entropy. So consider, for instance, the partition function at large n. So if you take the strict n going to infinity limit of the partition function, it basically has this property. When beta is bigger than pi over 2, it goes linearly with beta. When beta is less than pi over 2, it goes like 1 over beta. Beta equal to 2, so here, these are modular forms. Beta equal to 2 pi is basically the self-dual point. And from this, basically, you can infer that the density of states grows like the square root of the energy, which is the Cardy formula in a 2D CFT. And these are properties, basically, if you're doing ADS3 gravity, this is what we associated to the Hawking-Page transition, and these answers basically reproduce the area law of the BTC. Okay? So symmetric product orbifolds, from this point of view, if you're just interested in thermal properties of like just the partition function, you would have said, this reproduces the same physics as black hole physics. Okay? Highly non-trivial property that a symmetric product orbifold reproduces. And then again, it's completely independent of what you put there as a seed. The only thing that I'm assuming is that the seed is unitary and it has a gap between the vacuum and the next state, and you will be able to demonstrate this quite generally. Quite impressive for something that was not dual to gravity. Yeah.
This transition in the symmetric product, is it by the Hagedorn deconfinement?
Yes, it's a confinement-deconfinement phase transition.
Like in free field theory on S3, the people studied long ago, with the deconfinement transition, Hagedorn goes of states and then.
Sure.
N equals
Yeah, but this is,
three process.
yes, yes, exactly. It's exactly the same, and in higher dimensions, you would also attribute it from the point of view of the gravity dual to the Hawking-Page transition. But yes, this is a confinement-deconfinement phase transition that happens because you're taking n to infinity. So at any finite value of n, there's not a phase transition. It's only a phase transition when you take the strict n going to infinity limit. But yes, it's the same Witten 98 paper version in a CFT2. Yes. Okay, so that's quite impressive. Symmetric product orbifolds can mimic black hole physics. They can also do more than that. So something that we did very recently this year is that we looked at thermal correlation functions, okay, of single trace operators. So basically 2-point functions on the torus at infinite n. You get this beautiful answer, no matter what the seed theory is. That's the 2-point function that you get on the BTC background. So they don't just like give you like this Cardi-like formula. If you compute basically correlation functions of these light operators, you will get the same answer for the correlation function on the BT set. Okay? And this is basically telling you that you can, if you try to use basically properties of thermal correlation functions as an indicator that you have an emergence of space-time or that you hit a horizon, basically this is telling you you're kind of faking it in a sense. Okay? So these are theories for which, yeah, again, I don't care what you put here. You will always get this as an answer for a single trace, or even more generally, it will be for any light operator. Okay, and there's also quite a bit of universality in certain heavy light operators that correlation functions that we looked at. Okay, so it's quite impressive. These theories really do a really good job at trying to mimic gravity depending on the observable that you look at. And basically it gives you a lesson of what should we consider a stringent property of a CFT. Okay, so we have basically in terms of all the universal properties that symmetric product orbifolds satisfy, just as a summary of what I have presented to you so far, I've given you 3 properties that tell you how they mimic really well low energy gravity. So if you would have imposed these as basically holographic conditions, you would have said, oh yes, this is a holographic CFT. Well, no, because there's other conditions that tell you, no, actually, they're not going to be a low energy theory of gravity because of these other criteria. So in this context, you're trying to understand basically that there are some conditions that are necessary. For instance, you would have said that it's necessary that the thermal correlation functions match those of the BTC, but it's not a sufficient condition. Okay, so you can't list this as a condition that will unambiguously tell you, yes, you have a holographic CFT. Okay, so this is where the exercise starts coming in. Of like, when I list to you properties of what defines a holographic CFT, did you really find something that was just necessary, or did you find something that was sufficient? And a great place where to test it is in symmetric product orbifolds, because you will find that not all of these conditions are stringent enough. Let me see how I'm doing on time. So I have about 15 minutes, 10? Okay. You wanted time for questions as well? Okay. Okay. Okay, very good. So let's move now to the second part of the talk. I'll probably be done less than 15 minutes. So with that, you might say, well, then it looks like every symmetric product orbifold is the same. There's no difference between them. You will get all the same features. What was special, let's say, about D1, D5? Like, why was that like a lamppost to demonstrate it, ADS CFT, if I just given you a whole slew of properties where I didn't have to say anything about like some deep brain system, some fancy string theory? I was just doing conformal field theory and studying how these things behave at large n. That's all. Okay? So let's explore a little bit more then in this context. What does it mean for something to really have this these nice properties related to gravity, okay? And so here comes a more sophisticated version of how I want to understand symmetric product orbifolds. And basically, I want to understand their moduli space, and I want to understand if in their moduli space there can be a supergravity point. I'll refine this question a bit more as I go along. But basically, I want to see when a symmetric product orbifold could lead to something that is strongly coupled with a low energy dual, gravity dual, okay? And so I'll basically try to understand what are necessary conditions for this to go about, okay? And I identify which of these symmetric product orbifolds comply with them. Good. So let's draw two circles. So we have basically a space of theories that I'm calling holographic CFTs. This is what I'm trying to characterize and what I'm trying to design. And we know that there has to be various properties, some requirements on them. And on the other side, I have symmetric product orbifolds, which I think I already made a compelling case that they're not holographic, right? We're all convinced that they're not holographic. Yes, the circles do not intersect. Okay. Now, but I have a nail. I'll keep on hammering on it, and I have a hammer. So, like, let's keep on this story. Well, they're close. So now I drew them a little bit close together. But not just to kind of be like, well, but maybe there's something I could learn about holographic CFTs by having them a little bit closer together. And the way that I'm going to think about this is in terms of this moduli space. So by moduli space, I basically mean the set of exactly marginal deformations that I can have in a conformal field theory. And basically, the symmetric product orbifold theory, if I'm drawing here question marks because I first have to establish that this cloud exists. But basically, the symmetric product orbifold theory would have been something like a weakly couple point in this cloud because it was dual to something that it was tensionless. It looked like a free theory a bit. Basically, the copies were not interacting much with each other. So that's why I'm calling it weakly couple. It looks like floppy. But maybe I can turn on a marginal deformation, so that's what I'm labeling here by some operator that has conformal dimension 1,1, and that turns on some coupling. I turn on this operator with some coupling lambda, and maybe there's another point by turning on this deformation where the theory becomes strongly coupled, and that's my dual that has this low energy description, okay? This is the cloud that we've been taught in the context of the string theory constructions. Oh, there's a very fancy, complicated moduli space. Maybe, yeah, well, we have various indirect evidence that it's there and various checks. But, OK, maybe this is what's going on. And so now the question is, when can I really, when is this picture holding? OK, so when is the symmetric product orbifold something that I can deform and that I can connect to something that is strongly coupled? Okay, and so what we'll do now is focus on theories with supersymmetry with at least 2,2, because otherwise I don't know how to define the cloud. So I only know how to do it if I have enough supersymmetry to actually establish that the deformations are exactly marginal. And basically then what I'm going to do is try to find evidence for this point by looking at two criteria. So it's quite simple what I'm going to do. First, that the symmetric product orbifold has moduli, okay? That it has deformations, exactly marginal deformations, okay? That's my first criteria, so that at least this cloud makes sense. And then the second is that I'm going to look at quantities that are protected under the cloud. So there are certain quantities that will not depend on the coupling. And so if I compute them here, they should already have the features that I want at the strongly coupled point that should be compatible with gravity. And my favorite quantity in that context is what's called the elliptic genus. It counts a quarter BPS states. And this thing is very important also as well for black hole physics, but it basically has to satisfy, this elliptic genus will have to satisfy various of these sparseness conditions that I'm listing here, okay? Yes?
Does that mean that the correlation function that
Yes, which is very remarkable.
Yeah,
that because the operators, like even for protected operators, it's kind of weird. Like it's thermal correlation functions are not protected, like generically. So it's really strange that it's there. But yeah, we're very surprised about these results. It also has impact on like how you understand basically microstate geometries and a lot of the possible type program, because it's basically as well indicating that you have all the structure here, regardless of the details. But in any case, we'll look at these two basically properties here that are independent of the coupling, that I know from supersymmetry, that are independent of the coupling, and try to establish, will this give me a signal, okay? You might be suspicious based on what already happened to you. It's like, they're all going to be the same, right? Because everything that I've had told you so far holds for all of them. And here's where the surprises come about. So, as I said before, we're only going to consider CFTs that are unitary and compact. So you can try to generalize this for things that have a non-compact spectrum, but it's a bit more tricky. So let me keep my life simple. And again, we're going to consider theories that have at least 2,2, so that I have the confidence of these things being actually protected quantities. It will hold for 4,4 and higher, but yeah, and if you put 0.4, I'll get nervous, but in any case, there might still be things that you can say. Okay, now, out of this circle, actually, so this circle here illustrates all the possible symmetric product orbifold theories that you can do. I want to say first that actually the majority of symmetric product orbifolds will not have a moduli space, and the sense of having exactly marginal deformations. And the elliptic genera basically is going to not comply with what you expected from a holographic sense. So basically the elliptic genera will have this Hagendorn growth, because that was part of like all the states. So what I showed you in terms of the phase transition was that if you just computed the partition function, you had a Hagendorn growth. You might be hopeful that the elliptic genera, because you're counting less states, it should grow slower. Most of the time, the majority of the time, it does not. It still has a Hagendorn growth of states. And so from that point of view, it's a protected quantity. Move around how much you want. It's going to be Hagendorn everywhere in this moduli space, if the moduli space exists. Okay? So this is usually what's happening. Okay? So you grab, and we showed this. You can prove it, that most of the time, you're not going to get, the elliptic genus is going to be growing like Hagendorn. But there were some nice features, because again, we know that at least D1, D5 things worked. So at least there's one point in this circle that things should be okay. And so we actually found two different types of things that would happen that I'm illustrating here by these circles. And the sizes are a little bit characteristic of what's happening. So there was a small circle that we called type 1 theories, where you do have moduli. There are single trace twisted BPS states that could define my cloud. You don't need the moduli to just be, well, the marginal deformation, you don't just need it to be BPS. If you want to have this, this gravitational, this strongly coupled point, it's also important that the deformation is single trace, so it has the biggest effect at large N. And it's also good that it's in the twisted sector, so that it really makes the copies interact between each other. Okay? And if you look at the elliptic genera, they basically all have a growth less than Hagendorn, which was great, because that's compatible, and that was one of the first checks. Well, not the first, but it was an old check from like '99 of how the elliptic genera growth compared to the supergravity growth. And it has like the growth is much smaller, so it's compatible with a supergravity type growth of states. Okay? So what are the characteristics of this type 1? Well, the central charge of the seed always has to be less or equal than 6. guess what? The case of D1, D5 on K3, it's equal to 6. So when you were doing string theory, you're just at the edge, which is interesting. If the central charge is bigger than 6, then you're in the red zone automatically. So there's nothing else to discuss. When the central charge is between 1 and 3, our search is completely exhaustive. They're the n = 2 Virasoro minimal models, and they all fall into this classification here. Between 3 and 6, I don't have a classification of full supersymmetric conformal field theories between 3 and 6, but I can construct many. And we can basically check if they fall into here or don't. Okay, so if you present to me the CFT, our method basically we'll just go through quite quickly in showing this. Okay, it's interesting that there's not just so in the case of D1, D5, there's just a single deformation. Well, there's multiple of them because of supersymmetry, but it's basically just the Ramond ground state that is twisted. And here in these cases, there's more different types of deformations, so that's kind of fun. And there's also some multi-trace deformations that you can have fun with as well that are exactly marginal. Okay, 5 minutes. Great. Now, so that was type 1 here, the small little circle. Then what is this blue circle here? So this is what we call very cleverly type 2. So here, basically, there is moduli, so you can have an exactly marginal deformation that is single trace, twisted, and BPS. However, the elliptic genus still grows Hagedorn-like. So you have a cloud, but you will never have a strongly coupled point. So they will never be holographic in that sense. They will never lead to something that is holographic. It's kind of interesting also from the point of view of this criteria that demanding that you have a moduli space is not stringent enough because you can still not meet all these properties. However, I should say that out of all our searches, if you first demanded that the elliptic genus was sparse, you always found that there was a moduli space associated to it, which you could have thought that there wasn't. But in any case, there's a kind of hierarchy between these two conditions here. But this basically tells you something interesting also, that how the symmetric product orbifold will respond under a deformation will be very different, or there should be significant differences between the type 1 and the type 2 type theories. Okay. And this is basically where we are at the moment. So given this, given that, for instance, I have established that within symmetric product orbifolds, they're not all the same. There's some of them that could lead to something holographic, and they're in this little circle here. Would you have told me, this is enough, now we're done, this will lead to a holographic CFT, or what else do I need to do to convince you this thing will have a holographic CFT? Happy to hear what computation we have to do. They're all pretty complicated, the ones that I can think of, so that's why we haven't done much more, but any case. But it would be really nice if this was all I had to impose, and then this was sufficient criteria to lead to something where it had a strongly coupled point. But basically, now that I do have this, and I have candidate CFTs that did not come from a string construction, could you try to figure out what the gravity dual is with this information? So I'll give you all the chiral primaries. I'll tell you all you want to know about quarter BPS states. Is that enough to reconstruct a low energy theory of gravity consistently? I don't know, but they're out there. Okay, so defining gravity basically from the CFT. So now conclusions. Basically, my big question here, what I was starting with, was which classes of CFTs could capture classical and geometrical properties. I think, again, it's a difficult question, but it's something that now, with all the experience that we have on ADS CFT and all that we have done, I think we are in the right setup to push this further. And And I do think the answer to this is that symmetric product overfolds do teach us quite a lot about what it means to establish the correspondence and how to define it from one side to the other. Where you kind of can use this in two senses. So you can use it in a sense of like determining what things are not really very stringent conditions, because symmetric product overfolds will satisfy them. But then also, what are the more stringent conditions that should basically nail down what the definition is? Okay, and so and I think in this regard, based on the results that I have presented, what we need to understand better is to understand how these theories basically respond under the deformations. So explore the cloud and what these marginal deformations are doing. So with that, I conclude.